Welcome back. So we just figured out how long does this thing stay in the air. So what can we do with that? Let me clear all of this and redraw it, because maybe every time I redraw it, it might further clarify things. Actually, let me actually draw things a little bit fancier this time. So I have the ball, and it's moving. Look at that. Let me just draw the triangle ahead of time. And I'm going to use fancy. Oh, whoops. Actually, let me use a thicker line. So this was the initial vector that I wanted to do. Switch to green. This is its horizontal. I'm going to draw the arrows in a second. I just want to get all the line tool work out of the way. Bam. And then this is the close enough. And then if I use my paint tool, I could draw an arrow there, switch back to green, draw an arrow there, switch back to magenta, draw an arrow there. So this was 10 meters per second. 10 meters per second at a 45-degree angle. We figured out in the last video that its horizontal velocity is equal to 10 cosine of 45, which equals 5 square roots of 2. And we also figured out that the vertical velocity is equal to 10 sine of 45 degrees. 10 sine of 45 degrees, which also equals 5 square roots of 2. And we wanted to figure out how long does this thing stay in the air. And we said, well, if we're going, the vertical component is 5 square roots of 2 meters per second. So if I'm going 5 square roots of 2 meters per second, how long does it take for the ball to go from that point to the point that it's stationary at the top of its path? Right? So it's going at 5 square roots of 2 meters per second. And then it goes to 0, right? So how long does it take to decelerate from 5 square roots of 2 to 0? And there we just said, change in velocity. Well, my change in velocity is minus 5 square roots of 2. That equals acceleration, which is minus 10 meters per second squared times time. And we figured out the time to when the ball leaves to kind of its highest point is the square root of 2 seconds. And that happens if you just solve this equation. And that's how long the ball takes to go from the ground to its highest point, and it's going to take the exact amount of time for it to reaccelerate and come back down, right? So it takes square roots of 2 seconds to go up, and it's going to take square roots of 2 seconds to go down. So the total time is equal to 2 square roots of 2. Right? This is the total time. This is kind of a nice intermediate thing that we've discovered. Now, can we use this to figure out how far does that ball travel? How far is this sucker going to go? Well, the entire time that we were messing around with the vertical speed or the vertical velocity of this ball and the vertical acceleration, the vertical position, the whole time the ball was going up and down, it was also going to the right because it has this horizontal velocity, right? And we're going to assume that the horizontal velocity stays constant. And why can we assume that? Well, one, we're assuming that there's no air resistance, because air resistance makes things very complicated. And if this is something like a penny or a marble, it actually does have very little air resistance, so air isn't going to slow it down. And so if there's no air, what can slow it down in the horizontal direction? Well, nothing. Gravity only acts downwards, right? Gravity doesn't make something slow down as it moves horizontally. I mean, you can imagine pushing something on ice, and if there's nothing slowing it down, no friction, no air resistance, it'll just keep on going. And actually, what the assumptions we're making would be absolutely true on the moon, because the moon has no air. But anyway, so the whole time the ball is going up and down. It's also moving to the right at this speed, at 5 square roots of 2 meters per second. Right? And let me ask you a question. How long is it going to be moving to the right? Well, it's going to be moving to the right as long as it's up in the air. And do we know how long it's going to be up in the air? Well, yeah, we just figured that out, right? We figured out that it stays in the air for 2 square roots of 2 seconds. So to figure out its horizontal distance, to figure out how long it is along the ground, so we could say change in distance horizontally, or change in distance horizontally. That just equals my average velocity, which is just this, because it doesn't really change. So it equals 5 square roots of 2 meters per second times the time that I'm in the air times 2 square roots of 2 seconds times this sucker, 2 square root of 2 seconds. So when we multiply it out, let's see, we can say 10 times square root of 2 times square root of 2 is 2 times 2. So we go 20 meters. 20 meters. That, I think, is pretty cool. All I did is I said, well, I'm throwing something at 10 meters per second at a 45-degree angle. How far did it go? And now you could figure it out. You could figure out that it went 20 meters. And actually, you could do things the other way. I mean, we will, and I'll do that in future problems. You can figure out the exact angle you need to throw something, or you need to shoot something. If we were thinking military terms, if you were an artilleryman and you had to you had to figure out what angle to shoot the big gun at to shoot a target, I don't know, 5 miles away. Not that I advocate these type of things. War is very bad. You would be doing essentially this problem. I don't know if people in the military are actually doing it. They're probably having a computer do it for them, but it's really not that hard to do. And if we ever lose our computers and we have to do things with bows and arrows, it's good to be able to sit down and do the math like this. So that's all I'm going to do for, well, we could do a couple of other things too. We can also figure out how high the ball went. And how high the ball went is actually no different than the one-dimensional problem, right? We know that this is the initial velocity in its upward direction. We know it goes to 0. So its average velocity in the upward direction is going to be what? Its average velocity in the upward direction is going to be this plus this divided by 2. So the average horizontal velocity, vertical velocity average. I don't know. This is funny notation. It's just going to be half of this. It's going to be 5 square roots of 2 over 2. And it travels that for how long? Well, just while it's going up, it travels that for square root of 2 seconds times the square root of 2 seconds. Right? So distance is the average velocity times time. So this is equal, this square root of 2 times this square root of 2 is 2, and it cancels out with this. So the peak height that we could say, the height, is going to be 5 meters. So that's pretty neat. If I throw something at 10 meters per second at a 45-degree angle, its maximum height is going to be 5 meters, and it's going to go 20 meters. So I could draw that. Image, clear image. Image, invert colors. So let me draw my ground. Oh, whoops. So I'm going to draw my ground. It's kind of a yellow ochre ground. And I'm going to shoot something at an angle of 45 degrees at 10 meters per second. And we figured out that it will go 20 meters. And its maximum height is going to be, let's see, this is 10. So I'm trying to draw something kind of to scale. So its maximum height is roughly 5 meters. It is exactly 5 meters. Roughly is what I'm drawing. And so its path is going to look something like this. It's going to, right from the get-go, it's at that angle, but the angle is going to get shallower and shallower. Bam, it's the 5 meters, and it comes down, and then it hits the ground with, a thud. So there you go. We just figured out how far does that thing go, and how high does it go. What else could you want? So in the next video, I'm going to do this more generally so that we can kind of, we can work backwards. If we know how far something went and how long it was in the air, maybe we could figure out its angle. Or maybe we could actually figure out what the optimal angle is to throw something for distance. I'll see you in the next video.